Okay, so thank you very much introducing me, Kondo-san or Masaaki. And I'm Kentaro Sano, the leader of the architecture research group of this feasibility study. And it's my great pleasure to present feasibility study overview at the architecture research team in this feasibility study in person with you. Yeah. So this is the agenda of this talk. I'm starting with the overview of architecture research group, and then I'm gonna talking about the technological background and trend, feasibility study at the architecture research group in this feasibility study, including goals, concept, requirements, and architectural directions, and then I will summarize this talk. So first of all, I'm sorry, this is a bit busy slide, but I'm going to describe the overview of this architecture research group. So in this research or investigation, we are considering these four items. The first one is technology trends as status, which includes slowing down of Moore's law, as you know, and different silicon scaling rules from the previous ones, and the cloaking of existing approaches or architectures. But simultaneously, we also have new methods of semiconductor and packaging, such like 3D stacking or chiplets or something like that. And second one is international collaboration as strategy. So it should be essential to have technology collaboration across the borders because we have global supply chain. And it should be very difficult for Japan to cover all the technology by itself, especially for big, very complex computing systems, including fabrication to operation and including software development. And it's also very important to have some kind of differentiation through proprietary technology. And we also need to care about economical security of Japan. The third one is development and operation as request. And here we think that Fugaku Next should satisfy needs for science and technology industry and society of Japan. And then we need to consider the development, fabrication, and operation, which will be finally required around 2030. And of course, we also need to care about human resource development for advanced research and development in Japan and in the world, of course. The last one is versatility and high performance to be balanced as a goal of this project. And the Fugaku Next, the next generation of infrastructure should be available for a wide range of applications, including new trends such like AI or big data, etc. I'm sorry. And then we also need to pursue of ease of use for higher productivity. And of course, we need to achieve the required performance goal. So according to these items, we have been investigating based on these policies. So we investigate technical and strategic options for candidate systems, and we explore future technologies and architectures suitable for Fugaku Next, and we will evaluate their feasibility and effectiveness. And we will identify technologies that Japan should possess and develop on its own, and those that should be developed or introduced internationally. And we are investigating these technological items from elementary technologies and to system architectures. And we also need to conduct investigation with vendors, even with overseas vendors in HPC area, concerning development, fabrication, and deployment and operation. So this is the organization of this architecture research group. This group is led by me as group leader in RIKEN. And we also have 6 subgroups. And some of them are of vendors in Japan or in US. So let me introduce the technological background and trend, some of which are well known by you. So this is the very famous world ranking of supercomputers, top 500, and which is the ranking of HPL, high performance linear algebra or LIMPAC performance of distributed memory parallel supercomputers. And here we have #1 machine performance, and this is a sum of the all performances of all the machines in the list, and this is the 500th machine performance. And so this is the machines in the last decade, and as you know now, US Frontier is in the top of this list, but Fugaku is still in the second position in the list, while Fugaku is also in the number one position in other rankings, HPCC and Graph 500. And in this graph, we can see some trends of HPC technology. So first of all, the improvement ratio got slowed down around 2015. So we have some different line after that. Yes. And probably this is because of the slowing down of the Moore's law or difficulties in Moore's law. And we also have different architecture of supercomputers, mainly CPU-based and GPU accelerator-based. So in this feasibility project, we are targeting the future machine, next generation computing infrastructure, targeted around 2030. And probably we are targeting this performance range. But for this, we need to make a big jump from the present performance of Fugaku. But the real challenge exists in the system power consumption and performance per power, as you know. So this graph shows the average power consumption of the machines of top 10 machines and top 50 machines and top 500 machines. So all of them needed to increase for higher system performance. This is because of the limited improvement of performance per power so far, and we needed to increase the system power to increase the system performance, gathering more power. But remarkably, we have much higher system power in top systems. So in the case of Fugaku, so this is for the HPL, the entire machine operation power, but we consumed about 30 megawatts. And the present number of machine Frontier also consumes 21 megawatt. So we already hit the megawatt, tens of megawatt range for system power. But if we really consider sustained development goals and energy crisis that we are facing right now, we should cap the maximum power consumption of the system. So I think we cannot, or we should not increase the system power more. So then, now system power budget is the critical constraint of system performance. So what we learned from them, the insights, is as follows. The performance per power is now a key to achieve higher system performance, because the system performance is given by the system power allowed divided by performance per power of the computational unit. So, and as I mentioned, it's difficult to increase the system power infinitely, and we should have some cap on that. So how can we increase the performance per power? This is a critical question, and one of the primary goals in this feasibility study to find answers. So, and let me introduce rough projection of HP system performance summarized in NGACI white paper. So NGACI, this is the abbreviation of Next Generation Advanced Computing Infrastructure, is the activity to compile a white paper on technical issues and necessary research and development for future HPC machines and infrastructure through open discussion in the Japanese HPC community. So this activity was led by Kondo-san or Masaaki, and we also have worked together with these 4 working groups: architecture working group, system software working group, application library algorithm working groups, and system operation working group. And I'm here. The next speaker is here. So, and the white paper version 1.0 was already released, but I'm sorry, for this is only written in only Japanese, but it's already available, and you can translate it with DeepL or some AI machines. And version 1.1 will be released soon, I hope. This is the table of contents of the white paper, and today, I just brought part of the contents of this section, study of next generation system targeting 2028. Please note that in this white paper, this was written in 1 or 2 years ago, so we were targeting 2028, while in this feasibility study, we are targeting 2030. So we have a gap between them. So this is the rough projection of 2028 system performance. And so in this rough projection, we assumed processor categories of them. So LS, latency sensitive type of machine, and bandwidth-centric or throughput-oriented machine in BC. And last one is computer-centric machines, CC. And LS is of the CPU capable of CPUs capable of random memory access for typical workloads in especially in data centers. And such CPUs have large memory, large capacity, last level cache, deep cache hierarchy for smaller latency processing. An example of this type of processor include Intel Xeon, AMD EPYC, Amazon Graviton, etc. This is a high-end CPUs. The second one is of the CPUs and GPUs tuned for higher throughput for especially graphics, AI, and of course HPC. It should have a high bandwidth memory and throughput-oriented cache memory, local memory hierarchy or subsystems. And the examples include GPUs of these 3 vendors, and our Fugaku CPU, Fujitsu A60FX, with very long SIMD extension, and of course, Japan's NEC SX80 vector processors. The last one is computer-centric. This is processors targeting specific domains such as AI, such like Google TPU, Cerberus, Tesla, Dojo, Esperanto, Graph Core, Samba Nova, or something like that. So where we have a high density of operators on the silicon with very high bandwidth, only with on-chip memories, on-chip SRAMs. So which is a bit extreme cases. And how we project it, projection method is like this. So we estimated the peak performance of each system, and by targeting 2 nanometers node of TSMC fabrication technologies, and by using public information of it, and we extrapolated these specs based on current products, logic density, SRAM density, transistor power, transistor switching speed, etc. So I would like to, because of the limited time, I would like to skip the detail of derivation, but this is the result and the discussion. So, but please note that this is very rough projection and a bit conservative, I think. So we need to update the numbers based on the latest products. But we can see some relative difference or relative comparison between them. So, of course, the LS, high-end general purpose CPUs will have lowest number of peak performance, while the computer-centric should have the highest one, and we also have a very big gap between them, and BC gives the middle of them. And so these numbers are projections is of extreme estimation for these different directions. And at least we can say that LS, the high-end CPU-based, won't have sufficient performance improvement due to its limited performance per power. Okay, so we should explore hybrid architecture of BC and CC concerning target workloads and issues in programming. So let's see the comparison of state-of-the-art machines, Fugaku and Frontier. And I think Fugaku is of BC, bandwidth-centric CPU, with its very long SIMD extension and HBM2 memories. And I also think that Frontier is of LS-like CPU and BC GPU. And here we have AMD GPUs in the case of Frontier. Yeah. And please note that the use of technology is not so different than 7 nanometer for Fugaku and 6 nanometer for Frontier. Yeah. but we have a bit different numbers, especially for energy efficiency. Yeah, so Frontier has much higher energy efficiency than FNAC. However, FNAC also has big advantages in programming or productivity. We don't have to program any special kind of things for GPUs or accelerators. It's a big advantage, I think, for higher productivity. But for the next machines, we need to discuss the balance between the achievable performance and productivity or programming efforts or migration cost or something like that. So the insights learned from these discussions is that, the answer to the question how we can increase the performance per power, we should go for BC-like CPU at least with BC GPU or BC-like CPU, boundary-centric-like CPU with some more aggressive accelerator as computer-centric one, which are better, which works better. And any challenges of machines with BC, GPU, and CC, do we need to have some special programming model of them? And do we need to have higher cost of migration? And we have lower productivity? We need to transplant existing code to new programming model? And we also have another challenge of versatility in performance. If we use GPUs or some aggressive accelerators, can we achieve higher performance for the wider range of applications or very narrow applications domains? So these are fundamental questions that we need to know and find solutions or answers in this feasibility study. So in the remaining 4 minutes, I'd like to explain feasibility study itself at the architecture research group. So this is the goals of architecture research group in this feasibility study. So as goals, we identify promising architectures and system configurations for flagship machines that can be operational around 2030. This is a fundamental direction and goal. And for this, we will finally present conceptual design, system design plans, and provide a roadmap for development along with technical development issues. And we will also evaluate the criteria defined in this project for candidates, such as performance and power performance ratio, etc. And we also evaluate or estimate performance for target application defined in this project. That we will target the infrastructure toward research digital transformation infrastructure with advanced digital twin, which should have the close link of classical simulation, deductive simulation, AI or inductive simulation, and data infrastructure. And therefore, we need to target not only conventional HPC areas, but also new areas such as social sciences, such like digital twin or something like that. So what we'd like to investigate in this feasibility study is as follows. We would like to know what architectures and technologies are best and feasible. And we will set direction and requirements for them. And we will investigate the concept and the design candidates for its entire system, node, system, and microarchitecture, such like CPU, GPU, and others. And we will also investigate the available device and packaging technologies to be utilized, including advanced CMOS technologies, 3D stacking, and 2.5D chiplet technologies as packaging technologies, and silicon photonics. And we also need to investigate and system software to be developed, especially for accelerators or GPUs, if we adopt finally. And we also like to know the development roadmap and plan. And finally, it's also very important for us to know cost required for development and fabrication and deployment. So this is not fixed yet, but we are discussing the evaluation criteria, and this is their examples. So we will probably evaluate these items. The first one is technical criteria, which is broken down into performance criteria such like performance and performance by power, capacity, etc., scalability, etc., and functional or characteristic criteria such like versatility, programming productivity, interoperability, for trans reliability, etc. But we also need to consider, we should also consider strategic criteria for Japan, which should include spillover effect to science and industry in Japan and international collaboration, especially with US, I think. So probably this is the last slide, yes. So, and this slide shows the concept, initial concept, requirements, and architectural directions in this feasibility study. And so as initial concept and requirement, we are considering probably equivalent versatility to that of Fugaku, and with general purpose performance higher than that of Fugaku. Yeah, so most of application developers. But we also need to target sustained performance dozens of times higher than Fugaku for some specific application domains. So, and we think we should have system power similar to that of Fugaku, around 30, 40 megawatts at most. And if possible, we should have some extensibility of functions, and finally the system should be responding to new application fields such as social science, digital twin, and society 5.0, the new society with AI or digital twin technologies. And these are key initial architecture directions, but because of the time, I already passed 20 minutes, so I'm just explaining the first one. So we should have at least this paradigm shift in architecture and algorithm toward flop to byte. So we should focus on data movement efficiency. So we should design a performance power efficiency considering the efficient data movement on the chip or across the chips and internals, everything. So, and this is the initial Schroman architecture for future HPC, and where we have many 3D stacking technologies and silicon photonics and chiplet technologies, etc. So now we are working on with multiple vendors to find more aggressive and concrete technologies for future generation infrastructure. So this is my talk. Thank you very much.